Good day, we're reviewing Wetzel's Limnology textbook. This is edition number 4, and today we are starting chapter 11, Oxygen, with Raphael Marce, with the Catalan Institute for Water Research, Luis Gomez Gunner, with the Universitat de Girona, in Girona, Spain, and Kayelan C. Carey, with the Virginia Tech in Blacksburg, Virginia. All right. The oxygen content of inland waters. Oxygen is the most fundamental parameters of lakes and streams, aside from water itself. The rates of supply of oxygen from the atmosphere, photosynthesis, and water mass transport are counterbalanced by physical processes and consumption by biotic and abiotic chemical reaction. The interaction of all these biological, chemical, and physical processes within and among freshwater ecosystem results in a rich diversity of dissolved oxygen distributions in space and time. Their generating mechanism, description, and ecological implication are the main focus of this chapter. Oxygen content is related to a myriad of biogeochemical processes that control the concentration of substances. Dissolved substances such as, for example, dissolved metals, ecosystem functioning, and the usability of water for human purposes. Figure 11-11, so conceptual depiction of the processes affecting oxygen concentration in Arctic and Atlantic ecosystems. The plot summarizes the most relevant transport and reaction processes affecting oxygen dynamic in Arctic left side and Atlantic right side ecosystem, while processes toward the center of the plot are relevant to both types of ecosystems. The size of the arrows is proportional to the relevance of the process. In streams and rivers, advective transport and exchange with the atmosphere dominates. In lakes, advective transport is less important and stratification limits turbulent diffusion. The oxidation of reduced substances happens in lakes and river sediment, but can also occur in the water column if oxyclines are established. DOM is dissolved organic matter, as we saw before. So the left side is river-based, the right side is lake-based, and then the middle is pertaining to both, to a certain extent. And then the size of the arrows shows the importance of the process itself. So let's look at, for example, at the left side, which is the river-based. Atmospheric exchanges, very important compared to the lake. Photochemistry is important for both. Surface advection is very important in lakes. Not as important very important in rivers, not as important in lakes. And that is due to stratification and turbulence itself. Groundwater and aporeic flow. So you can see that there is a fair amount of importance of that, especially considering the proximity of the groundwater to a river system. And so we have oxygen production here through photosynthesis, as well as oxygen consumption through the respiration. And that is valid for both. Riverbeds, so we have, as well as in the sediment-based, for the lakes as well as for the rivers, we have oxidation of reduced substances at chemoclines. So, for example, we have reduction of these species, which is methane, we have ferrous iron, manganese, ammonium, hydrogen sulfide, hydrogen, etc. And then here on the right side, for lakes, we have internal waves being important, and then fauna and ventilation, which is not as important for the lakes, because probably the lakes, the rivers, because the rivers, they don't have as much fauna living on the side of rivers due to the scouring of the system under the kinetic energy, under the speed of the flow. All right. Dissolved oxygen is essential to the respiratory metabolism of most aquatic organisms. Consequently, environmental and water use regulations around the world almost invariably consider oxygen content as one of the master parameters to define threshold for ecological status. Low oxygen levels are generally associated with poor water quality and degraded habitat for organisms. Oxygen deficits are common in inland waters and have increased due to climate change and other anthropogenic pressures during the last century, necessitating oxygen monitoring at multiple temporal and spatial scales. Oxygen deficits are associated with events of hypoxia and anoxia when oxygen, so hypoxia is when oxygen concentration decreases below an acceptable threshold, and then anoxia is when oxygen concentration are close to zero. Okay, so anoxia is where there is no oxygen or close to no oxygen, and then hypoxia is when there's very little oxygen, but there's still some oxygen, and it's below a threshold for the studied environment or for the study process. For example, eutrophic streams exhibit large fluctuation of oxygen between day and night, and eutrophic lakes can exhibit high oxygen concentration in surface layers, but anoxic deep waters at the same time. Metric of oxygen content and deficits are thus a fundamental component of limnological studies. Following Hutchinson 1957, a skillful limnologist can probably learn more about the nature of a lake from a series of oxygen determination than from any other kind of chemical data. Such is oxygen's informative power for eliminating both the ecological functioning of the system and the suitability of water for human use. Processes determining dissolved oxygen concentration in inland waters are the net result of a complex interplay of physical, chemical, and biological processes operating at different spatial and temporal scales. This makes the interpretation of oxygen's spatial and temporal patterns a challenge for limnologists. Oxygen concentrations are highly variable, ranging from 0 to more than 20 milligrams of oxygen per liter in very productive waters. Under certain circumstances, such as water under ice in permanently ice-covered Antarctic lakes, concentration can reach as high as 50 milligrams per liter, measuring dissolved oxygen. Here we provide an overview of dissolved oxygen analysis as methods for measuring dissolved oxygen are reviewed in detail elsewhere. The foundation of historical oxygen analysis is the Winkler titration method and its numerous modifications, which has served as a benchmark for laboratory comparison and calibration of electrochemical, optical, and colorimetric techniques. However, advances in sensor technology during the last decades have now enabled reasonable, accurate, instantaneous measures of dissolved oxygen in the field and the lab, with an ever-growing diversity of sensor designs. For example, microelectrodes allow micrometer scale profiling in sediments and the water column, and some sensor design allow measurements of oxygen concentration as low as 10 nanomoles of oxygen per liter. These new sensor technology have greatly enabled high-frequency automatic monitoring of oxygen in inland waters, which has changed the way researchers and practitioners use oxygen measurement to solve fundamental and applied problems. Solubility of oxygen in water. Oxygen dissolves in water as a gas. Therefore, understanding the solubility of oxygen in water is of paramount importance to understanding oxygen dynamics in inland waters. Oxygen solubility is controlled by Henry's law, which we just saw in chapter 10, which states that the amount of gas that dissolves in water is proportional to its partial pressure, where C, so C is equal to Kh by P gas, where C is the solubility concentration at a fixed temperature, Kh is the temperature-dependent Henry's law's constant, and P gas is the oxygen partial pressure in atmospheres. For precise results, the effect of non-ideal gas behavior, density of water, salinity, and vapor pressure on Kh and P gas must be considered. For oxygen, these corrections are accounted for by nonlinear fits between the solubility concentration at 1 atmosphere and the combination of temperature and salinity. The solubility concentration of oxygen decreases non-linearly with increasing temperature and salt content. So as we saw on chapter 10, as you increase the water temperature, you decrease the solubility of a gas in the water. So colder water holds more gas than warmer water, as well as salt content, it appears. So as you increase the salinity, you also decrease the ability of a gas to dissolve in the water. Variation in atmospheric pressure also influence oxygen solubility concentration. At atmospheric pressures other than 1 atmosphere, solubility concentration calculated with equation in figure 11-2 should be corrected for atmospheric pressure. So I'll let you review those equations here. So the amount of dissolved gas is also influenced by the hydrostatic pressure exerted by the overlying stratum of water. If dissolved oxygen partial pressure in water is higher than the combined atmospheric and hydrostatic pressures, bubbles will form and escape to the atmosphere, removing gases from the water body. If the hydrostatic pressure is high, oxygen supersaturation relative to the atmosphere can occur without the formation of bubbles. The combination of atmospheric and hydrostatic pressure at a given depth is Pz is equal to P plus 0.0967 by the depth, where Pz is the hydrostatic pressure at the atmosphere, and then P is the pressure, and then the depth at which the sample is taken. P is the combined atmospheric pressure. Here we go. So the importance of the above relationship lies in its impact on absolute saturation concentration and its control of bubble formation. The oxygen concentration necessary for bubble growth increases with depth and hydrostatic pressure, and it is facilitated by turbulence and the presence of surfaces. As a consequence, bubble formation is more common in shallow waters of less than 4 meters. Oxygen bubbles can also form in the blood of freshwater animals if the solubility concentration suddenly falls due to a water temperature increase or pressure fluctuation promoted by extreme turbulence, resulting in gas bubbles trauma in fish and mortality events. So let's look at this figure here. Figure 11-2. Solubility concentration of dissolved oxygen in water at a pressure of 1 atmosphere as a function of water temperature and salinity. Okay? So the solubility concentration is on the y-axis. The x-axis is the water temperature. So as you go left, you decrease the water temperature, it gets colder. And as you increase on the y-axis, the concentration, the solubility concentration of oxygen increases. So, for example, for a parcel of water at 10 degrees centigrade, the solubility is about, let's say, maybe 8.5, something to that effect, for a salinity of 60, I believe. So let's see here. Yes, solubility, so let's make sure that we got this correct. The figure includes the equation and parameters necessary for calculating a saturation concentration from temperature and salinity. In waters showing specific conductivity below 2000 microsiemens per centimeter, S is equal to 0 can be used if very small errors are acceptable. In other situations, measured S, which is salinity in PSU, must be considered. So here we have, as I said, we have 10 degrees centigrade, we have a solubility of about 8.5 for a salinity of 60. And then we have a higher solubility of about, maybe about 12 milligrams of oxygen per liter for a salinity of 0. Okay? And then if we take really warm waters, let's say waters at 40 degrees centigrade, you see that we have a solubility of about 5.5 at a salinity of 60, and then we have a solubility of maybe 7.5 at a salinity of 0. So you can see that at lower temperatures, the difference that salinity makes is larger than it is at warmer waters, right? So as the water warms, the solubility is not driven as much by the salinity than it is driven by the temperature itself. A special case of the effect of solubility on oxygen levels is in permanently ice-covered lakes, where the exclusion of oxygen from the ice lattice as water freezes can result in very high oxygen supersaturation in the water below the ice. Oxygen saturation greater than 300% have been measured in these amectic lakes due to this mechanism. Solubility concentration is thus a convenient and important reference needed to interpret oxygen content because it provides a baseline that accounts for the effect of temperature, elevation, atmospheric pressure, and salinity on oxygen concentrations. This is why oxygen content is often reported as percent saturation with respect to the solubility concentration and atmospheric pressure at the surface of a water body. Because of differences in temperature, solutes, and elevation among water bodies, percent saturation can provide a better indicator of oxygen status in some cases than oxygen concentration. Water with oxygen concentration equal to the solubility concentration at the same temperature and dissolved solid content will thus be at 100% oxygen saturation, whereas water with an oxygen content half the solubility concentration will be at 50% oxygen saturation, and so on. Large deviation from 100% saturation indicate imbalances between processes producing and consuming oxygen. The dependence of oxygen solubility on temperature and salinity has important implication for the biogeographical distribution of organisms inhabiting inland waters, particularly for those requiring higher oxygen concentrations. The dependence of oxygen solubility on temperature also results in less oxygen available for organisms during the warm months, when metabolic activity peaks, which may lead to oxygen depletion and fauna kills. Oxygen exchange with the atmosphere. The bidirectional exchange of oxygen across the water-atmosphere boundary is frequently the most relevant process, affecting dissolved oxygen concentration in surface waters. The transfer of oxygen between the atmosphere and fresh waters is governed by the interplay of the partial pressure gradient with turbulent and molecular diffusion processes. Therefore, processes adding turbulence to the water, such as water currents, wind convective cooling, and surface and internal waves, are important drivers of water-atmosphere exchange. Other processes affecting the stability of the boundary layer usually play a minor role. Water atmosphere exchange by diffusion pushes oxygen content toward 100% saturation, either by increasing or decreasing its concentration. Air-water oxygen exchange rates are tremendously variable, but generally rivers and streams show higher transfer rates than Atlantic ecosystem because of greater turbulence. Considering gas transfer velocities in rivers and streams, atmospheric exchanges could range between 1 and 10,000 nanomoles of oxygen per meter square per hour, while in lakes, the maximum atmospheric exchanges rarely exceed 300 nanomoles of oxygen per meter square per hour. Bubble-mediated gas exchange also contribute to the air-water oxygen transfer. Breaking waves in lakes and high turbulence in streams help the formation of air bubbles that may exchange gases with the surrounding water before being released back into the atmosphere. This mechanism is particularly relevant in saline lakes, where the solubility of oxygen is low. In steep, turbulent streams, bubbles likely cause most of the gas exchange. An extreme case is waterfalls, where air bubbles can promote oxygen supersaturation. A similar process may also happen downstream of hydropower plants or spillways, which is a major cause of bubble trauma in fish. Bubbles rich in oxygen will typically form on the surface of photosynthetic tissues of freshwater plants and may eventually escape to the atmosphere. Very small bubbles can be stabilized by an adsorbed organic film and can accumulate on the water surface as foam. Oxygen can also be emitted to the atmosphere via methane bubbles generated in the sediment that entrain oxygen during their ascent to the surface. For example, oxygen ebullition is called. Those bubbles can contain up to 34% oxygen and can substantially contribute to oxygen exchange with the atmosphere in some cases. Advection, dispersion, and biota-mediated transport. Advection, the transport of a substance by the flow of water. Dispersion, spreading of a substance from concentrated to less concentrated area due to turbulent. Okay, so here we go. Advection and dispersion due to turbulent and molecular diffusion are the main transport mechanisms of dissolved oxygen in inland waters. Molecular diffusion is only relevant at small spatial distances or in situations where turbulence and advection are absent. The relative importance of the different transport mechanisms on oxygen concentration varies among water bodies and across space and time. For example, advection is usually more relevant than dispersion for the fate of oxygen in rapidly flowing rivers, while dispersion may account for most transport at the surface of a lake during very low wind conditions. In lake sediment, oxygen transport may be entirely controlled by molecular diffusion, restricting oxygen penetration to a few top millimeters of the sediments. In rivers, transport is influenced by local geomorphological characteristics such as slope, roughness, and meandering, which influence water velocity and turbulence and thus favor advection over dispersion. Other relatively small-scale features in rivers, such as the presence of logs, sandbars, or backwaters, influence dissolved oxygen concentrations by lowering water velocity and enhancing subsurface aporeic flow. This increases the residence time of water and solutes in the aporeic compartment, which can be responsible for a substantial share of oxygen consumption in river networks. In lakes, advection and dispersion transport is shaped by the overall water mixing and stratification dynamics of the water body. Pynoclines derived from heat distribution of dissolved and suspended solid may constitute formidable barriers for dispersion and even advective transport, constituting one of the fundamental causes of spatial and temporal oxygen patterns and resulting in the distinct oxygen regime described below. Subsurface flow are also frequent in lakes, particularly in human-made reservoirs, leading to metalimnetic maxima or minima. The transport of oxygen is also mediated by organisms. For example, burrowing fauna facilitate the diffusion of oxygen into sediments. These greatly enhance oxygen penetration, which increases aerobic respiration in surface sediments. In vegetated sediments, plants transport oxygen through the parenchyma, a spongy tissue that forms space-air channels in leaves, stems, and roots, which is eventually lost in roots, generating small oxic zones that exert strong control over sediment-dissolved oxygen dynamics. So let's see, why don't we leave it here, and tomorrow we'll start with the review of this figure here, figure 11-3, and we'll be starting this subchapter photosynthesis and photorespiration tomorrow. So talk to you soon. Thank you. Bye.